Hi, so today we're going to prove one useful proposition about complete Lebesgue uh, about Lebesgue Stieltjes measure. Okay, so let's get started. Recall that we can, so the definition for such measure is it is equal to the infimum of summation of mu of EJ where so let me write it out. So mu of f, recall, those are the review, okay? So this is equal to the infimum of infinite series of mu of AJ, BJ, okay? And sorry, this E. E is the subset of the union of AJ, BJ, okay? And then we also proved that mu of E actually can be approximated using open intervals. So rather than using H intervals, we can do open intervals. Okay. And then so proposition 1.18 has further claims. So the first claim that mu of f of E is equal to the infimum of mu of U, where U is open set contains E, and so U is open. And then the second claim saying mu f of E is equal to infimum. So we have infimum, we have a supremum of mu of K, okay, and then K is a compact set of E. So you can use H intervals to approximate the Lebesgue Stieltjes measure of E, or you can use open intervals. And here you can use open set, and here you can use a compact set. So let's give a proof. So we're going to prove first one. Since E is a subset of U, so U is open and arbitrarily chosen to satisfy this condition, okay? And then mu f of E is smaller or equal than mu f of U, and therefore we can take the infimum smaller or equal than infimum of this collection, mu f of U is open and U contains E. And then therefore we're done, okay? And then for the other direction, so since we need to use this result, okay? So it can be approximated by open intervals. For all epsilon larger than 0, okay, there exist AJ, BJ open intervals such that E is contained in the union of AJ, BJ, and this mu of AJ, BJ is smaller or equal than mu of E plus epsilon. And so notice that we also have, so we have this large or equal than mu of union of J of AJ, BJ, okay? And what is this? This is equal to denote this U. Okay, so for all epsilon larger than 0, there exists U, such U contains E, and the measure of U is less or equal than the measure of E plus epsilon. Okay, then, so we have infimum. So this is actually the definition for all epsilon there exists U such that U contains E, and the mu of U is smaller or equal than mu of E plus epsilon. That actually implies mu of E is the least upper bound of the collection mu of U, U open and U contains C. I'm sorry, I should write not least upper bound, but greatest lower bound, right? Let me think. Yes, greatest lower bound. So why? Well, we're already, let's see, what have we proved about? So here, notice that proved that mu f of E is lower bound of the collection, okay? And here I'm saying that if so here we're saying that if I consider mu of E plus epsilon, of course this is this, right? So we have this given. Then mu of E plus epsilon is no longer an lower bound of E, right? Since there exists U such that mu U is in that collection, right? Is smaller or equal than mu F plus epsilon. So this is not a lower bound of the collection. So I think the strategy to prove this, well, of course we want to prove, I think for me, I would set my strategy to be once I look at a problem and the problem is asking to show equality, then I will show separately, right? So here I show this inequality, and actually this inequality amounts to showing that this is the lower bound of this collection. So I don't have to write this line. I could just stop at this line. Why? Because I'm showing this is smaller or equal than this for every possible U that satisfy the requirement, which is U contains E and then U is open. So this tells me that this is a lower bound, okay, of the collection. And then the next step is to show, because I want to show something is equal to the infimum, of course, I'm going to use the definition for infimum. So there are two pieces for infimum. So if this is infimum of this collection, then first of all, this is the lower bound of this collection, which we proved here. And the second one is that we need to, prove that it is the smallest lower bound. It is the greatest lower bound, okay? What does that mean? That means if I have a number that is larger than mu of E, which is the lower bound here. If I have a number that is larger than this, then I can choose an element from this set, which is lower than that number, which means that number is not a lower bound, because if it is lower bound, then it should be smaller or equal than all of the elements. But I'm able to pick one element from this collection that is lower than that new number. Therefore, that new number is definitely not a lower bound of this collection. And this is what I did for the second one, right? I found the existence. Okay, so we're done with the first one. And then let's show the second one. So the second one is to show, this, right? Okay, so how to show this? Again, I'm gonna use two different steps. So the first step is one that is easier because we have K is smaller or equal than K the subset of E. So mu F of K is smaller or equal than mu F of E. Okay, and then because we have this, and then I can take supremum, right? So over all of this, you can do this or you don't have to do this to reach the conclusion that mu f of E is upper bound. So mu f of E, so I.E. is an upper bound of this collection, okay? And it remains to show it is the least upper bound of this, right? Which is to show that mu f of E is smaller or equal than the supremum, which is equivalent to show this. Okay, so let's discuss this. Okay, so first of all, notice that the measure E couldn't be unbounded. So, and why do we want finiteness? Because yeah, we want finiteness because we want to be able to deal with the informal argument. So once you have, if you have your set as unbounded, then that implies it's hard to do the subtraction later. So you will see. So define EJ is equal to define EN is equal to negative N comma N intersect so it's going to be intersect with E because E is unbounded, okay? Because E is unbounded, so what we are going to do is keep looking at this En. Why we like this? Because it has finite measure. It has finite, is bounded, right? Because it's bounded. It's finite. Okay, so then what will be the next step? What will be the next step? Take a look at define. Okay, so let's define UN to be equal to negative N comma N set minus En. So let this to be an open set that contains this. So if you want to look at the picture, for example, this is my negative N and this is N, and my E could be all over, right? It could be unbounded. So if I look at the set, and actually let me do, this is my E, okay, this is my E. And then negative N comma N intersect E is this region, right? Okay, and minus N comma N set minus En. Let me check. I think I made. Sorry, I think I made a mistake. So let's start. So define UN to be equal to negative N comma N set minus EC. Okay. Okay. If you want a picture, I can draw it here. I think should be an open set containing this, not equal, right? So I have negative N and I have N. And for example, here's my E. And then therefore, those are my EC, right? So set minus E, sorry, is going to be this region, right? Because this region. Okay, and I'm picking open interval. For example, this is UN. So that is like one example. Okay, and notice. So I'm going to notice negative n and so since UN is open and negative n intersect E is contained in UN, right? So by 1, there exists oh, I'm sorry. I think what is the result for 1? Mu f of E. Here's mu f of oh, okay. I think I messed up with so I want to, so let me just write it what I want to do. We want to apply 1 to find a desired open set that is not too big. So what about, so look at negative n comma n set minus E. So this is closed interval. So this is in f, sorry, mu f, and then this is in mu f, and therefore this is in mu f. And by 1, okay, there exists UN open, and UN contains this set with the measure of UN is smaller or equal than the measure of E plus 1/2 to the power of n. Okay, this is by 1. And then, yes, we obtain UN. Notice, so I'm going to, so notice that negative n comma n set minus UN is compact, and negative n comma n set minus UN is a compact set contained in E. So I'm going to illustrate by drawing a picture, which is very similar as the one I drew before. So if I have negative n and I have n, and this is my E, okay? And then this is my EC, right? Those are my EC. And I define UN to be an open interval. So those are the intersections, right? So those are the intersections. By intersection, I mean negative n intersect EC, which is this. Okay, and I find the blue interval is UN. Okay, and now if you look at this interval, set minus UN, right? Which is equivalent as intersect with UNC. So what is UNC? So this is UNC. So I'm looking at this intersect UNC, which is this region, okay? And because that this is compact and this is open, so this is a closed and bounded. So therefore it is compact. Okay, and then what we have is we have mu of UN, mu of negative n, n set minus UN is equal to mu of negative n, n intersect UNC, right? Which is equal to mu of negative n, n minus mu of negative n, n intersect un, okay? And because un, so negative n and intersect un is a subset of un. So by quantitative measure, the measure of this, sorry, the measure of this is going to be smaller or equal than the measure of this. And therefore, we have this, sorry, this is larger or equal than minus a larger measure, right? un. Okay. But we do have information that un is not too big, so it's going to be larger or equal than mu of negative n comma n minus mu of e plus 1 over 2n, and that is equal to mu of negative n comma n minus e. Let me think. Oh, right. So this is equal to because let me think. E intersect E. So this is negative n, and this is E. Oh, I'm sorry, I made a mistake here. So so there exists the UN open and the UN contains this set such that by definition of infimum and the result from part 1, this is smaller or equal than not mu of E, but mu of negative n comma n set minus E. Okay, I'm sorry. So what we have here is not minus, it's not that. So we're going to minus this. Yes, we're going to minus this, okay? And this is equal to, so, okay, negative n intersect E, right? Because this is equivalent as the measure of negative n and intersect EC. And, right, so minus 1 over 2n. And then you take the limit on both sides. So the limit of this, okay, is equal to the limit of this. Okay, and then this is equal to so this is equal to the mu of union n negative n continuity from below intersect E minus 1 over 2n. Oh, sorry, it's become 0. Okay, so we have mu of E, right? Because we have this since, so negative n set minus u is compact, and it is compact set that contains, it is a compact set and it is contained in E. Okay, it belongs to, okay, I'm gonna state in this way. So this were UN where for n in n is a subset of so mu of this, mu of k, where k is in E, and k is compact. Okay, so the supremum of this is smaller or equal than the supremum of this. And then what do we know from above is that since the limit of the limit of this is equal to mu of E, that implies mu of E, the limit point of this collection, right? Right. So mu of E is so how do I, so because we have the limit of this is equal to mu of E, that is equivalent as saying that for all epsilon larger than 0, there exists n for all n larger or equal than n mu of E minus mu of this is smaller than epsilon. So that implies mu of E is smaller or equal than mu of negative n sin minus un plus epsilon. Sorry, supremum. Okay, let's do this way. Minus epsilon, okay, is smaller or equal than this. So since so clearly, so we have shown that clearly mu of E is an upper bound of this collection, okay, of this collection. So together with 1, mu of E is mu of E is supremum of this. Hence, mu of E is smaller or equal than supremum of this. And earlier we showed that mu of E is larger or equal than that simply by the upper bound. So therefore, we have the equality. And we're done. Okay.